Bismillahirrahmanirrahim. Assalamu alaikum, students. In the last lecture, we discussed the topic virtual displacement, principle of virtual work. We could not discuss the D'Alembert principle because I lost my internet connection. I hope today I would be able to complete this topic. So today I am continuing with the previous lecture. So let me write the topic. So our topic is virtual displacement, principle of virtual work, and D'Alembert D'Alembert's principle. Let me make my pen a bit thinner. I think it's, and let me change my color. So let me use green. Not proper. I think I need this one is okay. So let me underline this properly. It is difficult to handle this pen. So I write here continued. So we're continuing with the previous lecture. So in the previous lecture, we first defined virtual displacement. We defined it as an infinitesimal displacement of a system, and that infinitesimal displacement in a system is a change in the configuration of the system as the result of any arbitrary infinitesimal change of the coordinates consistent with the forces of constraints imposed on the system at the given instant of time t. So there is no time elapsed during the virtual displacement. That's why we distinguish it from the actual displacement. In the actual displacement of the system, there is a time lapse that occurs during an interval of time dt. And during that time, forces and constraints may be changing, right? Then we wrote some equations. I will refresh your memory. First, we talked about the condition for a system in equilibrium. We said that if we have a system in equilibrium, then the total force on each particle on the system vanishes. Then the dot product of the force on the ith particle with the virtual displacement also vanishes. So then we summed over all these virtual works and we wrote this equation, summation I fi dot delta Ri. We named this as equal to 0 as equation first in the previous lecture. So this is Fi dot delta Ri is simply the virtual work of the force Fi, since we are assuming that the system is in equilibrium. So Fi dot delta Ri is 0. And if we sum over all parts of the system, all particles of the system, then we will get this 0. So this equation 1 is simply the condition for the equilibrium of a system written in terms of the sum over virtual works on all particles of the system. Then in the second equation, what we did, we decomposed the force on the ith particle into two parts. Let me use black here. So we wrote Fi, force on the ith particle, as sum of two terms, Fi A superscript A plus small fi. And this was our equation second. So Fi superscript A is the applied force on the ith particle and small fi is the force of constraint on the ith particle. So we used this equation second in first and wrote this condition for equilibrium of a system of particles as. So let me write this equation. Summation I Fi superscript A dot delta Ri plus summation I small fi dot delta Ri is equal to 0. So this is our equation third. Fi applied dot delta Ri plus summation I small fi dot delta Ri is equal to 0. Then we restricted ourselves to systems for which the net virtual work of the forces of constraints is 0. So we said if our system is such that this second term in this equation is 0, then the condition for equilibrium of a system will reduce to this first term equal to 0. So we wrote our fourth equation as summation I Fi superscript A dot delta Ri is 0. So this was our equation 4. This equation is called, as we discussed in the last lecture, principle of virtual work. It is simply the way of expressing the equilibrium situation of a system for which the net virtual work of the forces of constraint is 0, right? Then we moved to another point. We said that in this equation 4, there is no time. We want an equation which includes time so that we can discuss the general motion of the system through that equation. So we said that idea was used and thought by first James Bernoulli and developed by D'Alembert. The idea of D'Alembert was this: if we write the equation of motion for ith particle, we write Fi is equal to Pi dot, where Pi dot is the time derivative of the linear momentum of the ith particle. This is simply Newton's second law. Then we said we can write it as Fi minus Pi dot is equal to 0, which states that the particles in the system will be in equilibrium under a force equal to the actual force plus a reversed effective force. So Bernoulli and D'Alembert developed this idea of a reversed effective force. So minus Pi dot is the reversed effective force on ith particle. It is understood. So one way of saying that the system is in equilibrium, which we discussed at the start, is that force on each particle Fi is 0. Now, another way of saying the same thing is that the system will be in equilibrium under the sum of two forces. One force is Fi, and the second force is minus Pi dot, which is the reversed effective force. So instead of equation 1, we can immediately write, let me write here in black. So instead of equation 1, we can write summation I Fi minus Pi dot dotted with the virtual displacement delta Ri is equal to 0. This is our equation 5. See what we have done. We have replaced it in equation 1 Fi with the sum of two terms, that is Fi plus minus Pi dot. So equation 1 is the way of expressing the equilibrium situation of a system. Equation 5 is another way of expressing the same thing. So we have replaced one force by two forces. Now again in equation 5, we can resolve the Fi into two forces, applied forces and the forces of constraint. So let us do that. What we get? we get summation I Fi superscript A, applied force on the ith particle, plus small fi, forces of constraint on the ith particle. Then we have minus pi dot. So we had added the reversed effective force dot delta Ri is equal to 0, right? Or we can write it as, we can get applied force and force of constraint in two separate terms. So we can write summation I Fi applied minus pi dot delta Ri plus summation I Fi dot delta Ri. This is equal to 0. Fi superscript A is the applied force minus pi dotted with delta Ri plus summation I Fi dot delta Ri. Again, if we restrict ourselves to systems for which the virtual work of the forces of constraints vanishes, we can simplify this expression to just one term. So if the second term is 0, then we can write summation I Fi applied minus pi dot delta Ri is 0. I name this equation 6. Let me encircle it. So this equation 6 has a name. This is called the D'Alembert's principle. This is simply the way of writing the equilibrium condition for a system in terms of the virtual work, and we are assuming in it that the net virtual work of the forces of constraints on the system is 0. Now we will see what is the advantage of it over the equation principle of virtual work, that is equation 4. Advantage is that it contains time, it contains pi dot, and we can develop equations of motion from this principle. That's our next thing. So let me write the next subheading of this lecture. Euler-Lagrange equations of motion from D'Alembert's principle. So follow me cautiously. There is a chance of mistake because we have to handle many equations. So how can we now obtain Euler-Lagrange equations of motion from this D'Alembert's principle? First thing is, which you need to understand here, in equation 6, we have virtual displacement in Cartesian coordinates. And these virtual displacements, delta Ri, are not independent. So we have to transform these virtual displacements to the virtual displacements in generalized coordinates, which are independent from each other, so that we can equate the coefficients of delta Ri, I mean delta Qi, when we transform, when they are independent, to 0. That is the main thing. For that, what we do, let us proceed. So we have to now transform Ri to QG language. Let me write the transformation relation. We can write Ri as function of the generalized coordinates Q1, Q2 up to Qn and T. I name it equation 7. Assuming n independent coordinates, right? Now see what we do in order to go from Ri to Qj, transform these coordinates to generalized coordinates. We have to use chain rules of the calculus of partial differentiation. So we can write Vi as Vi is the velocity of the ith particle. So it is time derivative of the position vector Ri. Now using this transformation equation 7, I can write it this way. Summation K dou Ri by dou Qk dot plus dou Ri by dou T. This is my equation 8. Vi is d by dt of Ri, which is summation K dou Ri by dou Qk dot plus dou Ri by dou T. We have simply used the chain rule of differentiation, partial differentiation, and used equation 7. We want the total derivative of Ri with time. So we can see Ri depends on Q's and T. So first term is the sum, K, sum over K, some k runs from 1 to n because there are n q's, n independent coordinates. So in the first term, which is the sum in equation 8, we are actually finding how Ri changes with respect to q's, actually with respect to time, but we are using chain rule. We're first differentiating Ri with respect to the corresponding coordinate q, then multiplying with the time derivative of that coordinate. This is simple. Similarly, the arbitrary virtual displacement delta Ri can be connected with the virtual displacements in generalized coordinates. I can write delta Ri summation j dou Ri by dou Qj delta Qj. Let me name it equation 9. In 9, what we are doing? Delta Ri, my left hand side is the arbitrary virtual displacement in Cartesian coordinates, and my right side contains delta Qj, which is the virtual displacement in generalized coordinates. Now, in equation 7, see how Ri depends on Q's. So small change in infinitesimal change in Ri can be connected with the small change in delta Qj. We have to take all Q's into consideration. So first we find the partial with respect to J, then multiply the corresponding change in Qj. It is a sum. Now important is in equation 9 that there is no variation in time considered, because virtual displacement by definition considers only displacements of the coordinates. So let us move. Now, in terms of the generalized coordinates, the virtual work of the Fi, force on ith particle, becomes, so I can write summation I Fi dot delta Ri is simply what? It is the virtual work of Fi summed over all particles. So I can write it this way: summation I comma j Fi dot dou Ri by dou Qj delta Qj, which can be further written as summation j Qj dot delta Qj, let me call it 10, where Qj are called the components of the generalized force, defined as summation I Fi dot dou Ri by dou Qj. Let me name it equation 11. Let me first check it. So first is summation I fi delta Ri summation ij fi dot dou Ri by dou Qj delta Qj. So you can see we have simply used equation 9. So we have replaced delta Ri by this dou Ri by dou Qj delta Qj, and there is summation over J, right? So we have actually, remember in equation 6, I have to ultimately operate on this D'Alembert's principle. In this equation 6, first term is Fi dot delta Ri, right? So that is my left-hand side. And next thing you need to understand that I have now left the superscript A. It is understood now in D'Alembert's principle when I write summation I Fi dot delta Ri, this Fi is the applied force. So I have not written here the superscript A. Now what I did in this virtual work expression, I have replaced the infinite this virtual displacement in Cartesian coordinates to virtual displacement in generalized coordinates, making use of my equation 9. So this okay. Let me check it. Then we write equation 10 where we define Qj with summation I Fi dot dou Ri by dou Qj, and they are called the components of the generalized force. Let me write components of generalized force. So we have made adjustment in the first term in equation 6, that is D'Alembert principle. We have written it in terms of Qj, that is generalized force, that is equation 10. Now we will turn to other term involved in equation 6, D'Alembert's principle, which contains Pi dot delta Ri. So let us do that. So other term in equation 6 may be written as, we can write summation I Pi dot dotted with delta Ri. We can write it this way, summation I M I Ri double dot, take care of the dots, dot delta Ri. Check it, we can write it. Summation I Pi dot delta Ri, which is the second term in equation 6, D'Alembert's principle. So we have written it this way, summation I Mi Ri double dot. Ri double dot is the acceleration. When we multiply it by Mi, that is the force, and Pi dot is also the force. Now, using 9. This becomes, let me, using equation 9, which equation 9? Which changes delta Ri to delta Qj. That is this one. When I use equation 9, I can write it as summation I comma j mi ri double dot do ri by do qj delta qj. Right? So we have here replaced delta ri by summation j do ri by do qj delta qj. So we've used 9, right? So let us move. So let me here write equality. So where this is actually equal to what? Summation I pi dot delta ri. So first it is equal to this, then using 9 it becomes summation I j mi ri double dot do ri by do qj delta qj. And let us move. Next step. Now consider now the relation. Summation I mi ri double dot do ri by do qj. I can write it. Summation I, let me write it first, d by dt of mi ri dot do ri, this here dot is important, do ri by do qj, then minus mi ri dot d by dt of do ri by do qj. We check it. We name this equation 12. Let me check it first. Summation I mi ri double dot do ri by do qj is equal to summation I d by dt of mi ri dot do ri by do qj minus mi Ri dot d by dt of dou Ri by dou Qj. Summation I is outside the whole thing on the right hand side of equation 12. This left side, this relation is simply the portion of this above equation. In the above equation, we have this MIRI double dot. So this is this portion. Let me encircle it. This is this portion, including the summation. MIRI double dot dou Ri by dou Qj. Now think how it is equal to, think about equation 12 right hand side. My first term contains product of two functions. So when I differentiate them, I will get this term plus this second term. So I've subtracted this term in order to get back my left hand side. So think about this. Think about this. Now, in the last term of equation 12, where I have first time derivative, then I have to partially differentiate Ri with Qj. So we can interchange the differentiation with respect to T and Qj. So I can write, this piece, this piece, where's my pen? This piece. In this piece, I have first differentiation of Ri with respect to Qj, then with respect to T. What I do, I interchange the order. I write, we can write d by dt of dou Ri by dou Qj as dou by dou Qj of Ri dot. Let me change the color of my pen. Keep the track of equations. Don't lose your focus. Then I can write it this way. I can write summation k dou 2 Ri by dou Qk dou Qj Qk dot plus dou 2 Ri by dou T dou Qj. I can also write it equal to dou Pi by dou Qj. So let me check it. So first we wrote d by dt of dou Ri by dou Qj as dou by dou Qj of Ri dot. So we have interchanged the order of differentiation. First we differentiate Ri with respect to time, then with Qj. Then in second step, what we did, we wrote, we actually used equation 8. This equation 8, where we can write this Ri dot as this sum. Check it. So here I've used using equation 8. Let me check it. Summation k dou to ri by dou qj dou qk qk dot plus dou to ri by dou t dou qj. Then I can write it dou by dou qj of vi, because ri dot is the velocity. Further, from equation 8 we can write. So let me write it on next page. Also, from equation 8 we can write dou vi by dou qj dot is equal to dou ri by dou qj. Let me name it equation 13. Dou vi by dou qj dot is dou ri by dou qj. Go to equation 8 and check it. This is my equation 8. I am differentiating vi with qj dot. So second term in equation 8 has no contribution. First term has contribution. So you will simply get dou ri by dou qj. So we get equation 13, dou vi by dou qj dot is dou ri by dou qj. Now substitution of these changes in equation 12 leads to using substituting these changes, all these changes which we discussed. Let me write it, I will figure out. Substituting these changes in equation 12, we have, let me change the color here again. Use this color. So substituting these changes in equation 12, we get this summation I mi ri double dot dot dou ri by dou qj is equal to summation I dy dt of mi vi dot dou vi by dou qj dot minus mi vi dot dou vi by dou qj. Let me check it. Mi summation I mi ri double dot dot dou ri by dou qj is equal to summation I d by dt of mi vi dot dou vi by dou qj dot minus mi vi dot dou vi by dou qj. Let us move to equation 12, see what we have done. This is our equation 12. So what we have done, we have first replaced here here ri dot with vi, and here dou ri by dou qj we have replaced by dou vi by dou qj dot, which is our equation 13. And here we have again replaced ri dot by vi, and here what we have done, we have written it as dou vi by dou qj, that is we have changed the order of differentiation, which was our equation. Which equation was that? That was our equation, this one. We can write d by dt of dou ri by dou qj as dou vi by dou qj. So we have here replaced this thing by dou vi by dou qj, right? So we reach it here now. Now the second term on the left hand side of equation second, this all thing, this all expression is pertaining to the which term? It is pertaining to this term, that is this is pertaining to the second term, that is pi dot. Now all what are we doing? We are actually operating on the Alembert's principle to get the equations of motion. That's our equation 6. Where is my equation 6? This one. Now this second term, let me write, then I will explain. Now the second term on the left hand side of equation 6, which is D'Alembert's principle, can be written as, second term on the left hand side of equation 6 can be written as, let me write it, summation j, then I have d by dt of dou by dou qj dot summation I of mi vi square then minus dou by dou qj of summation I of mi vi square outside we have delta qj Let me check it. Summation j d by dt of summation j is outside the whole thing. D by dt of dou by dou qj dot of summation I half mivi square minus dou by dou qj of summation I half mivi square times delta qj. What we are doing, we are saying that second term, that is this one. Second term of equation 6, that is summation I pi dot delta ri. First we showed that that is equal to this whole thing. So this whole thing to equation 12 is portion of that second term. Then you have to multiply it by delta qj to get the full term. Equation 12 is the portion of it. So when you make these all changes into use, I'm saying this equation, the second term on the equation 6 can be written as, you check it at home, this is your home assignment, check it. At home. Now, summation I half mi pi square is simply the kinetic energy of the system. We write it as T. What is it? It is the kinetic energy of the system. Kinetic energy of the system. So therefore, D'Alembert's principle that is equation 6 becomes. Now we collect all things together. So let me write it in different color. So it becomes summation j d by dt dou t by dou qj dot minus dou t by dou qj minus qj delta qj is equal to 0. This is my equation 14. Summation j d by dt of dou t by dou qj dot minus dou t by dou qj minus qj delta qj. See what we have done. We have first replaced it here by a summation I half mi vi square by t. So this becomes, but this is the second term. Then we have first term in equation 6, which is this one, which is ultimately qj delta qj. Then we have multiplied this equation 6 by minus So we have made this term negative and second term positive that we can do. Our right hand side is 0. So we got this. Right? d by dt of dou t by dou qj dot minus dou t by dou qj minus capital Qj whole times delta Qj is 0. But you can see thus far in obtaining equation 14, we have made no restriction on the nature of the constraints other than that they are workless in a virtual displacement. I've assumed that first. Now the variables Qj in equation first can be any set of coordinates used to describe the motion of the system. Now if the constraints are holonomic, however, then it's possible to find the set of independent coordinates Qj that contain the constant conditions implicitly in the transformation equations. And then any virtual displacement delta Qj is independent of any other virtual displacement delta Qk. And therefore, the only way for equation 14 to hold is for the individual coefficients to vanish. By that I am saying, if this Qj, let me use here pen. So if these virtual displacements are independent, which you can do, you can choose your generalized coordinates such that they are independent of each other. Then this summation will be 0 when the coefficients of delta Qj are all equal to 0. That means this whole bracket should be 0. That is d by dt of dou t by dou Qj dot minus dou t by dou Qj is equal to capital Qj. This is my 15. D by dt of dou t by dou Qj dot minus dou t by dou Qj is equal to Qj. And we know we have n independent coordinates, so there will be one such equation for each coordinate. So in all, there will be n such equations. Now let us move further. Now, if the forces are derivable from a scalar potential function V, if the forces are derivable from a scalar potential function V, then force on the ith particle will be equal to minus del V subscript I on the ith particle, and the generalized force Qj can be written as I can write generalized force Qj as summation I Fi dot dou Ri by dou Qj. This is my generalized force. So what I do, I write it minus summation I del V, referring to ith particle, dot dou Ri by dou Qj. Let me check it. Qj summation I Fi dot dou Ri by dou Qj. So we have used the definition of the force in terms of the scalar potential function V. We have replaced Fi by minus del IV. So it is minus summation I del IV dot dou Ri by dou Qj, which is exactly the same expression for the partial derivative of this function. Let me write it, which is exactly the same expression for the partial derivative of a function minus V scalar potential, function of positions R1, R2 up Rn T with respect to Qj, with respect to Qj. So I'm saying Qj is minus dou V by dou Qj. Let me check it. It is exactly the same expression for the partial derivative of a function minus V of R1, R2, Rn T with respect to Qj. So I'm saying equation 15, not 15, this equation Qj is equal to this thing is same as Qj equal to minus dou V by dou Qj, where V is function of positions and time. So you will check this at home. This is your assignment. Check this at home. So we can now, for this case where we can derive force from a scalar potential function V, we can replace Qj by this partial derivative. So let me use another page for that. Therefore, equation 15 can be written as, we can write 15 as d by dt of dou t by dou Qj dot minus dou by dou Qj of t minus V is equal to 0. I name it 70. d by dt of dou t by dou qg dot minus dou by dou qj of t minus v is equal to 0. Now, here we have defined the scalar potential V as functions of positions here r1, r2 up to rn. When you make this substitution for the partial derivative, you check that. So our V does not depend on the generalized velocities. Let me write here our V does not depend on the generalized velocities. Therefore, we can include a term in equation 17 containing the partial derivative of v with respect qj dot, because that term is 0. Our v does not depend on generalized velocities. So let me use this color. Therefore, I can write d by dt of dou by dou qj dot of t minus v. Then I have minus dou by dou qj of t minus v is equal to 0. So what we have done, we have added one additional term in equation 17. That term is the partial derivative of v with respect to generalized velocity dou qj dot. Here we have actually dou t by dou qj dot, but I have written here dou by dou qj dot of t minus v. So I have added one partial derivative. Because that is 0, v does not depend on the generalized velocities. So that's not going to affect our equation 17. Now we have d by dt of dou by dou qj dot of t minus v minus dou by dou qj of t minus v is equal to 0. Now we define a new function. As you all know, we define L as t minus v, which is called Lagrangian of the system. So therefore, let me call it equation 18. So therefore, we can write d by dt of dou L by dou qj dot minus dou L by dou qj is equal to 0. This is my equation 19. Let me encircle it. D by dt of dou L by dou qj dot minus dou L by dou qj is equal to 0, where L is t minus v. We have here in equation 17, first added this term, then edit the partial derivative of v with respect to generalized velocity. Then t minus v we replaced by L. So we reach it here. Let me call it equation 19. So these are Euler-Lagrange equations of motion. As you know, Euler-Lagrange equations of motion. Of course, there is an equation in each generalized coordinate. If you have n independent coordinates, you will have n equations. And one note you need to think about this. For a particular set of equations of motion, there is no unique choice of Lagrangian such that equations 19 lead to the equations of motion in the given generalized coordinates, right? So there is no unique choice of the Lagrangian that you need to understand. This is how we obtained the Euler-Lagrange equations of motion from D'Alembert's principle. So this is all for today. And before leaving you, I will just give you this summary. So first we defined virtual displacement, then we wrote condition for the equilibrium of a system. Then we separated our force on the ith particle into two parts. Then we reached to the principle of virtual work, equation 4, which is simply saying that the condition for the equilibrium of a system, provided the net virtual work due to forces of constraints is 0. Then we introduced the idea of reversed effective force and reached to the D'Alembert's principle. Then this is also the condition for the equilibrium of a system, in which the net virtual work of the force of constraints is 0. Then our purpose was, you see, all this was to get rid of this delta Ri into delta Qj, this, because we can make these coordinates independent and equate the coefficients individually to 0. For that all thing what we did was done. So we transformed our coordinates from Cartesian to generalized coordinates, used the chain rule for partial differentiation, and transformed the virtual displacement in Cartesian coordinates to virtual displacement in generalized coordinates, talked about the generalized force. Then we reached here where we said if forces are derivable from the scalar potential function V, then this Qg will disappear, then there will be potential. Then another thing, in equations 19, we assumed that the potential is independent of generalized velocity. So this is all for today. Wherever I have given you the assignment, for example, here I told you check this at home. Somewhere I told you think about this. Do all the assignments and don't forget to like, share and subscribe my channel. Assalamu alaikum. Thank you.